Well, hi again, everybody. My name is Greg Anderson, and this is the Good Timekeeping Show with Greg Anderson. Today, I want to talk about timekeeping technologies through the ages, starting with ancient times, okay? How did people keep track of time? Basically, I've made this point in the past. Timekeeping is really based on solar astronomy, so observing what the sun is doing from sunrise to sunset. When does the sun reach its highest point in the sky every day? And we base our timekeeping off of that. I think that in places where the civilizations are near the equator, there wasn't as much variation in how early does the sun come up and how late does it go down. Maybe throughout the year, from the winter to the summer, the shortest day, as it were, only had maybe an hour less daylight than the longest day. And so they were able to divide their daytime into 12 pieces because they liked to use base 12 back then. And then they could kind of figure that the nighttime hours were about equal. So you'd have 12 hours of daytime, 12 hours of nighttime. And I think that's kind of the origins of our 24-hour clock as we still use it today. But how did they keep track of time? Well, you can keep track of, when does the sun come up and go down, and you can kind of figure out when it's at its highest point in the middle of the day. But how do you track the hours in between? And so there were some ingenious ways this was done, not the least of which was just using what many of us think of as a sundial or a shadow clock. Now, I experimented a little bit here at my own house with creating some sort of a sundial, and all I really needed was something that would stick up vertically and cast a shadow, and then I made marks down on the ground of where that shadow was at different times in the day. Now, I can use a reference of my quartz watch or my phone or something to figure out, and I can go out there every half hour, every hour, whatever it is, and make a mark on the ground to show where the shadow was. And what I would find is that the next day, at the same time of day, these different shadows would line up and match up pretty well throughout the year. So you could use that to keep track of the time. And if you divided, the day up into 12 hours, and you were near the equator, you'd do pretty well keeping track of time using your own shadow clock, or again, what we call a sundial. But it doesn't work on cloudy days, and it doesn't work, at night. And it doesn't work as well in places where daytime and nighttime, or the amount of time that the sun is up changes drastically as you get farther away from the equator. So day to day, the length of day, as it were, of daylight would change quite a bit. So there are a few other things they came up with in ancient times. Probably one of the simplest ones was the water clock. So imagine, if you will, you've got something that catches your water and some source of water where the water is pouring in at a consistent rate, whether it's fast or slow, it's just consistent. And then you've got some markings on the containment vessel here, so you can mark the passage of time by how much the water has built up. So if I were to do this, if I just had someone hired to be my royal timekeeper, for example. Oh, and I'm messy here, spilling water all over the place. I think I would not qualify as the royal timekeeper with such a mess that I'm making. But you get the idea. As this pours in, let's say it takes, half hour, hour, whatever it is, to pour that and fill it up. You would just kind of keep watching that, keep pouring until until it goes up, and then you'd say, well, the official time is whatever it is. Or, maybe something a little bit better, something like this where, it can drip at a more consistent rate, and then a little bit more slow, a little bit more precise. And if this were happening and someone were in charge of keeping this consistent, then you could use the water basin to kind of figure out how much time had passed. And that was, again, in ways much more sophisticated than what I've demonstrated here. That was one way that maybe ancient folks could have kept track of time, using water pouring into a place where they could measure how much water was coming in. So that would be the water clock. Now, something else that worked out pretty well was the a candle clock. So this one wouldn't be perfect for that because it's kind of tapered. But imagine if the candle were consistent in its diameter from the base to the top. And imagine if I had observed this well enough that I could tell how much time it took for a certain amount of the candle to burn away. So the materials I'm using are consistent, the shape and size of my candles are consistent, and then let's say I could just mark it. Let's say every, every 2 inches, I'd make a mark on there, all right? And then I would know, let's just pretend that for every 2 inches, I know that it takes an hour for the candle to burn 2 inches off. So, I could put some marks on my candle here and keep that consistent there. And then, I would light the candle, and every time it burned away to the next mark, I would know that an hour had passed. Maybe I want to do, half hours as well. So I go ahead and make my marks here in between my hour marks. And, I would have my half hour marks for my candle. And of course, I would have experts who really knew what they were doing to make my candles and keep track of time using the marks on a candle. So that was another, fairly effective thing. Again, it's consistency. If this is burning at a consistent rate, then you could use that to mark time. And this would work, whether it's daytime or nighttime. Just make sure you don't blow the flame out. It would work when it's hot or cold outside. The candle, the water clock, you might have trouble in the wintertime when your water is freezing or the flow is not as consistent. Your water source might not be the same flowing into your measuring basin, but the candle clock could be more effective than that. Something else that we've all kind of heard of, but maybe not many of us use anymore, would be something like this hourglass here, or kind of a sand timer. So as you can see, what this is a sealed container that has dry sand inside, and in theory, that it goes from the one larger part down to the other larger part. It has to pass through this small restriction in between them. And with any luck, this will fall from the top to the bottom in a consistent manner, so that when this is done after, say, an hour, and all of the sand has gone from the top to the bottom, then you just simply turn it over and start timing a new hour. This actual hourglass was a gift from a friend of mine, and I've appreciated this. It's just a nice, elegant thing to do. I will have to say, though, if you're into atomic timekeeping, it's not exactly as precise as you'd want it to be. I think the last few times I've timed this, it takes 62 or 63 minutes for all the sand to go from one end to the other. But I suppose if this is your primary timekeeping source, then maybe being 2 minutes off out of an hour is not something you need to worry about too much. I'm going to do my yoga for an hour, and I'll use this. And so what if I'm 62 minutes into my yoga before I stop, rather than 1 hour? So again, an elegant timepiece. Just well self-contained, and because this is a sealed container here, the sand doesn't get wet inside. There's nothing to make it inconsistent. It works pretty well no matter the temperature or humidity on the outside, because I've got this just dry sand inside. And I pretty much know that, the worst thing about a sand clock like this is sometimes, when it gets down really close to this top part being empty, it's like there's not enough pushing down to make the rest of it go down. You don't have that whole container of sand pushing down to make sure it's still going through this little restricted part in the middle. So sometimes it seems to stop a little bit early, and you got to kind of tap it or shake it a little bit to make sure that the rest of the sand goes down. But again, if you're using this to time your precise scientific experiments, then well, maybe you should consider getting something else for timekeeping. Out of all of these solutions for timekeeping, I think the shadow clock, or some of these solar observatories that we still see today in the form of obelisks in Egypt, or something like Stonehenge, which started off as some sort of a solar astronomical observatory. Those things are still around, and amazingly, if you know how to read them, they still work, because the movement of the Earth relative to the sun has not changed. And as I said, our timekeeping is really based on solar astronomy and observing the sun and its positions, and how relative to what we're seeing, how all that movement changes over the course of a full year. But here we're looking centuries and millennium after some of these things were put in place, and they still seem to be tracking okay with showing us solstice and equinox times and all that sort of stuff. So the shadow clock is probably the most enduring out of all of that stuff. However, like I said, it is limited to not working very well at night, or on a cloudy day or something like that. So it wasn't until we get into later centuries that the mechanical clocks started to come into play. And really, it was during the 17th century, or should I say the 1600s, that mechanical clocks, as we know them today, started to really have their roots, where some of these ingenious folks were coming up with the mechanisms that are still in use today, as far as the concepts and principles are concerned, where you had pendulums and gears and things that would then show on kind of a round face of a clock and display the time based on weights and pendulums and springs interacting with each other. And again, it's about these movements being done at a consistent rate that we can observe and measure. So whether it's this, where we're watching sand fall through this at a consistent rate, or we're watching water go into a vessel at a consistent rate, or we're watching a candle burn at a consistent rate, the key to our mechanical clocks and watches is being able to make some sort of mechanical movement that happens at a consistent rate that then we can use to measure time with. And so when you talk about pendulum clocks, those were kind of the most accurate clocks around from the mid-1600s all the way up into the 20th century, up into the 1900s. A good clock with a pendulum on it was something that would give you your best accuracy in the most practical manner. But there was a little bit of a problem within all of this, because again, you get into the 1600s, 1700s. Suddenly, folks wanted to travel on the open ocean a lot more than they used to before that. So 1492, you got the voyages of Columbus that kind of showed the world that, the shape of things is a little bit different than what you might have expected before that. So all of a sudden it was like, everybody wanted to sail around and see the world and go places. And if you're in the middle of the ocean on a big ship, it might be a little bit of a concern to you of where are you and where are you going? And so navigation became a very important thing. Okay, so they used sextants and different devices to look at the stars and look at the sun and figure out where they were relative to the land that they were seeking. So it's pretty easy to figure out where is east and west using say a compass, magnetic compass, and just watching where the sun is going, coming up and going down. Then you could also figure out north and south, and then again using stars and the sun position itself, you could kind of figure out where you were, especially when it came to how far north of the equator are you, how far south. But the difficult thing to figure out was how far east and west. So one of the things they were able to do as a reference was try and figure out, well, let's say you've left England, and you know what time it is in England, and you know what time the sun is supposed to be in a certain position in the sky in England. And if you know what time it is, and then you observe where the sun is where you are, you can do the math and figure out how far away am I from England, because in England the sun would be over there, but since the sun is here, then that means I must be over here. And this the kind of math that they don't teach us in school anymore, but navigators on a ship knew how to figure all that out. But the problem was, how do you keep precise time on a ship, especially if the most precise way to keep time is a clock with a pendulum? Imagine if I put my grandfather clock in a ship, especially the old ships they were using, way back in the Pirates of the Caribbean days, right? So if I've got my grandfather clock in a ship like that, and I'm relying on that pendulum making a consistent swing back and forth, but the ship itself is rocking all over the place, backward, forward, side to side, then my pendulum is not going to swing at a consistent rate anymore. And my wonderful clock that works great on dry land is not going to keep very good time in a ship. So it was kind of an urgent thing to figure out how to come up with a clock that could keep good time on a ship with all the movement of the ship. How can you come up with a clock that's going to still keep accurate time when the clock itself is moving so much? And so this became a thing where the royalty in England actually created a contest and offered a big cash reward for the inventor who could come up with the most precise chronometer that could handle the movement of a ship, and therefore making navigation on the open ocean much more precise than it used to be. And so there's a big story about how that happened and who invented the technology and whether they were given proper credit and whether they were given the proper cash reward that they were supposed to give. I think the cash reward finally did arrive many, many years after it was deserved. But that's a whole story you can get into. But I think that the key to that is this is where we see the first iteration of how timekeeping and precise timekeeping was essential to precise navigation. So, okay, they figured this out, hundreds of years ago, and all of a sudden, they could sail around the ocean and using their clocks and using what they were observing for the position of the sun and the stars and everything, they could really be very precise about where they were in the ocean and where they were going so they could get to where they would want to go and not get lost. But you had to have an expert navigator to make all of that happen. Now, I'm going to fast forward to, we got into more precise clocks like quartz clocks and atomic clocks. And the fascinating thing about atomic clocks is that once again, we see the way that accurate timekeeping is actually at the heart of our most precise navigation systems. So if you're familiar with, for example, the global positioning system, the global positioning satellites, GPS, what is that? You've got these satellites out there, tens of thousands of miles in orbit. So they're out there pretty far. They're much, much higher out than, say, the space station, okay?
These GPS satellites.
Hang on a second. Let me interrupt here because there's something I want to clarify that's interesting here. The orbit of the International Space Station is about 260 miles up. So to scale with this globe, that would be about that far up. And so that's the orbit, and it's going at a speed that makes a complete orbit about once every 90 minutes or 16 times in a 24-hour period. The orbit of the global positioning system satellites, to scale with this, it's about 12,500 miles up. So that would be about this far up for your GPS satellite. So, and it orbits, one of those satellites would be about 2 orbits a day. So about 12 hours per orbit. And what about something like your Dish Network, DirecTV? If you're getting satellite service from something like that, then the orbit for one of those satellites is about that far out. Okay, and these satellites are positioned in such a way that as the Earth rotates, the satellite follows and just kind of synchronizes with that rotation, so that from your perspective on the ground, it looks like the satellite is in a fixed position, and as the Earth moves, satellite moves with you. And so, if you just point to one spot, like your satellite dish does, then the satellite that it's trying to get will always be in that position relative to where it's pointed. So a little bit about satellites. I just thought that was something worth clarifying. These GPS satellites, and so what they're doing is they are transmitting time code from their various clocks. There are clocks on board those satellites transmitting back to the Earth, just time streams, okay? Well, other information as well, but primarily time streams. So you have, say, your little handheld navigation device, your little GPS receiver in your car, or maybe a handheld thing, and this is receiving time information from these satellites that are, thousands of miles out there. And by comparing, and here's the deal, these clocks on board these satellites are to be perfectly synchronized down to minuscule fractions of a second. So your little handheld device is picking up the time code from that satellite, where, all these different satellites, and comparing the difference between the time that it's receiving. So it's able to say, well, the time from that satellite is just a little bit ahead of the one from that satellite. So that means that where I am, I'm closer to that satellite than I am to that one. And by comparing the different time streams from various different satellites, you get a more and more precise idea of where you are in relation to those satellites. And then calculating where those satellites are supposed to be, you can figure out where you are on the surface of the Earth. And again, it's all based on time. And it's also pretty astonishing to me to think that you have this device that can be relatively cheap and so small that you hold in your hand that can pick up time data from so many satellites, process that information so quickly and so precisely to the point where it can actually overlay your location on a map inside the device. It's astonishing that something that powerful is something you can hold in your hand or put on the dashboard of your car. And it's precise timekeeping that's at the heart of this modern navigation system that we use in our modern world. And just like, back in the ocean-going days, where they were looking for the best chronometer to keep time to help with navigation, now we have the best clocks that we've come up with so far in satellites that are helping us navigate, and that's a pretty astonishing thing that we're able to have. So I've taken you all the way from shadow clocks and sundials up to atomic clocks in satellites, and well, I think that's pretty astonishing that we've come this far together. And I don't know what's coming up next. When I was at the National Institute of Standards and Technology coming up on a few years ago, one thing that they were talking about was the ability and the technological development of smaller and more precise atomic clocks. Something that rather than having atomic clock receiver in something that you could hold in your hand, how about having an actual atomic clock device that's small enough to be in a handheld device? And when that sort of thing is ready for prime time, as they say, you're going to start seeing self-driving cars, for example, that can calculate all this time data to place themselves precisely in a lane of traffic. To what now your handheld device might be accurate to within a few feet. How about being accurate to within just a few centimeters? And now you've got a self-driving car that can be exactly where you want it to be on the road. This is the kind of technology that we're looking forward to in the near future. That's all based on timekeeping. So anyway, that's all for now, and I hope you will join me again for another episode of The Good Timekeeping Show.